Every day, we're bombarded with contradictory claims. A new superfood cures disease, a morning routine guarantees productivity, and competing models predict entirely different economic forecasts. The universe is inherently noisy. Reality throws billions of random data points at us every second. To survive, the human brain evolved to be a pattern recognition machine, eagerly connecting dots and inventing narratives even when there is nothing there but pure chance. This leaves us with a serious problem. When a clinical trial shows a new drug working or a city's crime rate drops, how do we know if we've uncovered an actual rule of nature or if we're just staring at a random fluke? If you rely solely on human intuition, you are going to guess wrong. Our gut feelings are simply unequipped to handle high-stakes medical, policy, or business decisions in a chaotic environment. To fix this, early governments developed a tool meaning description of a state. Looking at this 1665 document, the Bills of Mortality, we see the blunt origins of statistics, states counting citizens, births, and deaths to track population and taxes. Over the centuries, this practice evolved from simply keeping tallies into a rigorous mathematical discipline built on probability theory. Mathematicians realized they could quantify random events and measure uncertainty itself. Statistics became a technology designed to extract reliable information from raw noise. It gave researchers a mathematical framework to account for observational errors and natural variation in their data. Today, this discipline is our core epistemological tool. It is the agreed-upon method we use across the sciences to prove what is actually real and what is just an illusion of the data. We cannot survey every person on Earth, and we cannot test every atom in a crystal. Because we cannot measure a total population, we have to extract a smaller, representative sample and study that instead. This animation shows how descriptive statistics organize that sample. We take a scattered mess of raw measurements and build a distribution curve. We look for this central tendency, often the mean or median, to find the most typical value in that group. But we also have to measure the dispersion or variance. A wide, flat curve means the measurements vary wildly from that center. A sharp, narrow peak means almost every member of the sample behaves the exact same way. Descriptive statistics give us a perfect summary of the data we've collected, but they cannot tell us if our specific sample accurately represents the rest of the universe, or if we just happen to pick a weird batch. To bridge that gap, we use inferential statistics. This is the mathematical framework that allows us to take a small sample and safely deduce the properties of the much larger population it came from. The foundation of this process relies on a concept named by statistician Ronald Fisher, the null hypothesis. This is the baseline assumption that there is absolutely no relationship or no change between the variables you are testing. Here you can see the trial of the data. Researchers run tests to see if their sample is extreme enough to prove the null hypothesis false beyond a reasonable doubt. If the data pushes past a specific boundary, it achieves statistical significance. But there is always a risk. That highlighted area at the extreme tail represents a type 1 error, a false positive. This happens when a random statistical fluke tricks you into rejecting a null hypothesis that was actually true. Conversely, if the threshold is too strict, you risk a type 2 error, or a false negative. This is where your data falls just short of significance, causing you to dismiss a real, valid discovery. Modern data scientists also use an alternative called Bayesian statistics. Instead of a simple pass or fail test, a Bayesian model continuously updates a hypothesis's probability of being true every time new evidence is collected. Inferential statistics never delivers absolute 100% certainty. Instead, it provides a mathematically precise measurement of our doubt. Because that inherent uncertainty is always present, valid statistical research does not give you a simple yes or no answer. Instead, statisticians use this bracketed range called a confidence interval. Rather than claiming an exact number, a 95% confidence interval tells you that if you repeated the exact same study 100 times, the true population value would fall inside this range 95 times. Openly acknowledging a margin of error and defining its exact mathematical limits is the ultimate hallmark of scientific rigor. However, because statistics relies on probability and sampling, it can easily be weaponized. Through biased sample selection,
poor experimental design, or stripping away context, these tools can be used to tell damned lies. The most common trap in media and public policy is the assumption that correlation implies causation. Just because two trends vary together does not mean one is causing the other. Consider these two rising trends. They look perfectly linked. But if we pull back, we expose a lurking variable, a confounding factor secretly driving both. Without accounting for that unseen variable, conclusions drawn from the first two lines are entirely wrong. This is why statistical literacy is our greatest intellectual defense mechanism. You have to know what is missing from the picture. Understanding the science of uncertainty empowers you to stop blindly consuming facts. It gives you the tools to question the sample, challenge the hypothesis, and navigate a complex world with skeptical clarity.